Okay, today we're talking about the nuts and bolts of quantum mechanics. This is really cool stuff. It's really amazing and important stuff in modern physics. It's the core of how computer chips work and all kinds of practical things, and it will blow your mind. However, it's going to take us a little while to get through it, so this is going to be a little longer video. But just so that you know what you need out of this, what you need to work the homework is different from what I'm going to tell you much more than you need, because this is really interesting, and I think you need the context to really appreciate and understand these things, but the actual technical things you need to know to work homework problems in this unit are a lot less than what I'm going to tell you. So just so you know what to look for if you get lost, there are three basic things you need to understand in order to do the homework. First of all, I'm going to give you an equation that relates energy and frequency for a quantum particle, and I'm going to give you an equation that relates momentum and wavelength for a quantum particle. Alright? The next thing, we're going to talk about uncertainty relationships, both for classical waves and for quantum waves. You need to know those. And then finally, you need to know how to figure out the allowed energies for hydrogen atom states, and how to figure out what wavelengths of light are emitted when a hydrogen atom makes transitions between two particular states. Alright? But now let's get into quantum mechanics. Alright, so quantum mechanics sort of started with the quantization of the photon that we studied last time. The next big step is when Louis de Broglie was thinking to himself, and he said this thought came to him like a bolt out of the blue. And this basically what he thought was something along these lines. If light, which we thought of as a wave, can also behave as a particle, then maybe things we think of as particles can behave as waves. Alright? So that's kind of a crazy idea. And so basically he says, well look, maybe things that we think of as particles have a wavelength and they have a frequency. And maybe we use the same relationships we would use for a photon of light for these other particles, right? So for a photon of light, we said that its energy is related to its frequency with this equation, and its momentum is related to its wavelength with this equation. All right? So de Broglie says, look, the energy, frequency, and momentum wavelength relations for an electron, a proton, an apple pie, or a Ford Taurus, also, maybe they obey these equations. And it turns out that he was right. Okay, but one little note here. Apple pies don't travel at the speed of light. So sometimes when you're calculating the energy of a photon, I'm going to put a little gamma here to say this is the energy of a photon, that's equal to hf, and then you say, well, f is the speed of light over the wavelength, right? So I can also write this as hc over lambda. That works for a photon. It does not work for a Ford Taurus or an apple pie or an electron because they don't travel at the speed of light, all right? So be careful. Don't get used to doing this with photons and then use this for a massive particle or a Ford Taurus, all right? This is only for light because the light travels at this speed. What you want is this equation here in terms of the frequency if you're trying to find the energy of an electron from its frequency or its frequency from its energy. All right, this equation's good, but as soon as we wrote f as c over lambda, we were assuming we're talking about photons. So don't get those mixed up. If you want to know the wavelength of an electron, instead of using its energy, we'll use its momentum. We'll use this equation here. So these are your basic equations that you need to remember. Okay, so if an electron is a wave, if a Ford Taurus is a wave, what exactly is it that's waving? For a photon of light, it's a combination of an electric and a magnetic field that are oscillating. You can measure these fields directly if the frequency is small enough. If I have radio waves, which are made up of very low energy photons, right? I have a radio tower, the radio waves come, I can put up an antenna, I can measure those waves directly. All right, for visible light, it oscillates too fast for current technology to measure the wave oscillating directly, but we can see that it's a wave indirectly by looking at interference, right? But for massive particles like an electron or an apple pie, it turns out the waves, you can't measure them even in theory. We know these waves exist, but you cannot directly measure them. In fact, these waves are complex. They're not even real waves. The thing that's oscillating is a complex number. So how do we know that these waves even exist? Well, we can measure them indirectly. How might I verify that a Ford Taurus is a wave? Interference or diffraction, right? I can indirectly tell that it's a wave by looking at wave-like properties. Okay, so let's imagine I want to do like a two-slit interference pattern for a Ford Taurus, or a diffraction grating, making a pattern for a Ford Taurus. Well, let's think about this. I need to have a grating whose slits are spaced, by something on the order of a wavelength, right? What is the wavelength of a Ford Taurus? Well, remember, our equation for wavelength is h over momentum, all right? And assuming my Ford Taurus is not moving at relativistic speeds, we can approximate its momentum as just being mv, right? So h over mv. Well, the mass of a Ford Taurus is about 1,000 kilograms-ish, all right? The velocity, how fast? Well, the bigger the velocity, the shorter the wavelength. So let's try and make the wavelength bigger by assuming kind of a smallish velocity. Let's assume that we're only moving 1 millimeter per second, all right? You plug that in, and you find out that your wavelength is 4.4 times 10 to the minus 34 meters. And that's because this constant, Planck's constant, h, that we discussed last time, it's really small, right? So, how are we going to make a diffraction grating to diffract our Ford Taurus if that's what the wavelength involved is? It's going to be pretty hard, right? And that's why we didn't notice the wave nature of matter earlier, because the wavelengths involved are just too small. It might as well not be a wave, right? But now consider something really tiny. Instead of a Ford Taurus, let's consider an electron. Imagine I've got an electron with a kinetic energy of 10 electron volts. It turns out, right, the mass of an electron is really small. You calculate the velocity at 10 electron volts. It's pretty fast, but it's not enough to rain on our parade, because the mass of the electron is so darn small in SI units. And it turns out that the wavelength of our 10 electron volt electron is 0.39 nanometers. That's still pretty small, right? That's about 1,000 times smaller than the wavelength of visible light. So how am I going to make a diffraction grating to diffract electrons? Well, where have we seen something that small before? Well, it turns out that this is, a fraction of a nanometer. That's a typical spacing between atoms in a solid. So maybe, rather than trying to make a slit in aluminum foil to diffract my electrons, maybe I could use the atoms themselves in a piece of aluminum to diffract the electrons. And it turns out you can do that. The first time something like that was done by Davisson and Germer. They were able to diffract electrons off of a piece of metal. It wasn't aluminum, it was nickel, but it's the same idea. All right, and the electrons scattered off of the different atoms. And you have these different atoms, and in certain directions, the reflections off of the different atoms add constructively, but those directions depend on the wavelength of your electron's waves, right? So they're actually able to see the diffraction pattern of the electrons bouncing off of their nickel atoms. And we're able to show, that electrons actually behave like waves. All right? This is not the only experiment that's been done showing that matter behaves as waves. There's been a lot of experiments done since then. In fact, I've been involved in several of them. As a postdoc, before I came to BYU, I worked on an experiment at Yale in which we made an interferometer with cesium atoms. So instead of splitting light waves and making them interfere, we split the quantum wave of cesium atoms and made them interfere. All right, so the idea was our cesium atoms come in, and we would actually use light beams to split the cesium atoms and make the wave travel two different paths, and then at the end they would come together and interfere. And this plot down here, this is actual data from the experiment showing interfering cesium atoms. That's an interference pattern. All right, so cesium atoms behave as waves. When I was a graduate student, I worked on something called Bose-Einstein condensation. And what we did is we took a bunch of sodium atoms, a little gas of them, and we'd cool them down to be really cold. We made two of these little condensates, Bose condensates of sodium atoms, and then we let them go. We let them expand into each other. And you know what we saw? We saw interference fringes. So here's a couple pictures that we were able to take of our cesium atoms as they expanded. We just shot a laser beam through them. It was on resonance with the transition in the cesium. So if there's a lot of cesium atoms present, they absorb, and where there's not a lot of cesium atoms, it lets the light through. And by looking at the shadow, we were able to see that there were places with lots of cesium and places without a lot of cesium. Sorry, cesium without a lot of sodium. We did these experiments with sodium. The interferometer before was cesium, this is sodium. All right, so we're able to see an interference pattern. We're able to see that our sodium atoms were behaving like waves. All right? So an atom is a little bigger and more complicated than an electron. Turns out you can do even better than that. Anton Zeilinger's group in Vienna some time ago, they were actually able to do a two-slit interference pattern with buckyballs, carbon-60 molecules. So a molecule with 60 atoms, all right? That's 60 times bigger than one atom, right? Now, you'll notice his interference fringes aren't quite as sharp as the ones I showed you in the previous slides. That's because this is a much harder experiment, all right? Remember, as the mass gets bigger, the wavelength tends to get smaller. But that's not the only problem. Not only do carbon-60 atom molecules have more mass, they have more degrees of freedom too. And it turns out your molecules have to be in the same state or they don't interfere. It's kind of like light. If I send light through a double-slit aperture, but one of the slits rotates the polarization of the light by 90 degrees, the light from the two slits can't interfere anymore. They can't cancel each other out anymore. All right? So you have a similar problem here. You got to make sure that your buckyballs are all in the same state. They're not vibrating in a different way or something, or else it kills your interference. So really hard experiment, but they made it work, and now we know that carbon-60 molecules also behave as waves. The presumption then is that everything behaves as waves. All right. So if everything behaves as a wave, if you're a wave, if electrons are waves, if chocolate chip cookies are waves, what does that mean? What does it mean to be a wave? Well, one interesting thing about waves is they aren't confined to a particular spot, right? If you saw a wave on the ocean and I asked you, where is that wave? You'd say, well, it's wavy. It's kind of not in one place. It's kind of spread out, all right? A pure sine wave exists everywhere, right? If you were to plot a sine wave, a pure sine wave, you'd have to keep plotting forever because a sine wave never dies off. It goes on forever, all right? So this is what a sine wave looks like. I'm looking at a piece of it, but really it just keeps going on and on, right, off the edge of the screen and so forth. All right? It goes on forever. Now, over here is a power spectrum. I'm going to take my pure sine wave and I'm going to calculate a power spectrum of it, and I get this. What is a power spectrum? A power spectrum basically shows me, in order to make some waveform, what sine waves do I have to add together to get it? And to get a pure sine wave, I only have to add one sine wave in. So when I plot my power spectrum as a function of wave number, right, there's only one wave number because there's only one sine wave in my sine wave. All right? But now imagine, if you will, I have a shuttered sine wave. So it's not really a sine wave. It's like a sine wave, except I'm setting it to 0 outside of this region. So now I have something like a sine wave, but it's localized. Well, this isn't really a sine wave, right? Sine waves go on forever. But it turns out I can write this as a sum of sine waves, such that the sine waves all interfere. I mean, the sum interferes destructively and cancels out outside this region. All right? If I calculate the power spectrum of this, how much do I have to add of different sine waves in order to get this? The power spectrum I get is this, right? It's a spread. So a sine wave that exists everywhere only has one sine wave in it, one wave number, one wavelength. But a sine wave that doesn't exist everywhere, that's not really a sine wave, we chop it off, now it's got a spread of wavelengths in it. It's not just one wavelength, not just one wave number. All right, here's a Gaussian. It looks really thin, it's hard to see, but I'm just plotting this function right here. All right, it's called a Gaussian. All right, if I draw the power spectrum of them, what sine waves do I have to add together to get that? It turns out the power spectrum looks like this. It's a broad range of sine waves. Now, here is a similar thing. It's also a Gaussian, except this Gaussian is wider, all right, than the previous one. This one's very narrow. This one's much wider. Look at the power spectrum. When I make the Gaussian wider, when the wave is wider, this power spectrum gets narrower. So here I had a narrow pulse of wave. It involved a broad range of sine waves. Here I have a broader pulse, and it involves a narrower range of sine waves. All right? Here's a femtosecond laser pulse. So here's the electric field oscillating plotted as a function of time or position for a pulsed laser, all right, a really short pulse. And it's got some power spectrum. I can add a bunch of sine waves to get this. But the point is, in order to make my wave exist in a short amount of space or a short amount of time, I had to add together a lot of sine waves to do that. And it turns out we get what's known as the uncertainty principle for a classical wave. And the uncertainty principles basically say, in order to make a wave that only lasts a short amount of time, it takes a spread of frequencies to make that happen. And the product of those two has to be greater than or equal to 1/2. So The shorter I want my pulse to last in time, the broader range of frequencies I'm required to add together to make that short pulse. So if you want to snap your fingers and make a really short sound, that snap has to involve a lot of frequencies. If you have some speakers on your radio at home and you want it to reproduce a really short pulse of sound, those speakers have to be capable of reproducing a broad range of frequencies, all right? Because a short pulse involves a broad range of frequencies. Likewise, if I want to have something that's a very pure frequency, I want something that's really close to a sine wave. I want something that is almost just one frequency, has very little spread in frequency. That has to last a long time, all right? So if I sing for 1 second, right, that limits how pure my tone can be. And if you wanted to define my pitch of my voice very precisely with, with very little uncertainty in the frequency, it requires me to sing a long time, all right? There's also, if we look in time and frequency, we can also think in terms of space and wavelength, although we typically do it in terms of 1 over, or 2 pi over the wavelength, the wave number, right? If I want to have a pure sine wave that just has one wave number, just one wavelength, all right, that means delta k is 0, which means delta x has to be infinity. A pure sine wave has to exist everywhere, all right? If I want to have something that lasts that just exists in a short space, in space, a wave, I drop a pebble in the pond and I say those ripples are contained in a very small area, all right, a very small distance. To have a wave that's confined in a small distance, it must be composed of a broad range of wavelengths, or a broad range of wave numbers, all right? And that's the uncertainty principle. So these are 2 good equations you ought to know, all right? This is useful. If you want to make something that lasts a short amount of time, it requires a spread of frequencies. If you want something that exists in a small space, it requires a broad spread in wavelength or wave number. All right? So that's what it means. One thing it means to be a wave is that the uncertainty principles apply. So let's apply the uncertainty principles to a quantum wave. All right? So our classical wave, we said delta omega delta t has to be greater than or equal to 1/2, and delta x delta k has to be greater than or equal to 1/2. All right? In quantum mechanics, let's do the energy one first, right? We learned that the energy of a photon and the energy of an electron, it has to do with the frequency of the quantum wave, right? Remember Planck's thing, E is equal to hf, all right? Well, f is just, so this is just h times omega over 2 pi, which is h bar omega, all right? Where did h bar come from? H bar is Planck's constant divided by 2 pi. So if E is equal to hf, it's also equal to h bar omega, all right? So if I plug in, if I solve this for energy, right, or sorry, for omega, I'm going to say omega is equal to E over h bar. So if I have some spread in frequency, that means I have some uncertainty in the energy, delta E over h bar. I plug this into this equation and I get the equation delta E delta t has to be greater than or equal to h bar over 2. So what does that tell me? This is really useful. For example, an atom emits light. How long it takes to emit the light determines how well defined the energy of the light is. An atom, I put an atom in an excited state. How long does it stay in the excited state? If it doesn't stay there very long, then the energy of that excited state is not very well defined. If I want to measure the energy of something very precisely, I have to take a long time to do it. All right? What about position momentum? Well, it turns out that the wavelength, right? We said that the wavelength is related to momentum. So without doing this here, just giving you the answer, you can figure it out yourself. It turns out you can write this equation for a quantum particle as delta x delta p has to be greater than or equal to h bar over 2. So what does that say? If an electron is confined to some space, its velocity, its momentum is not well defined. There's some uncertainty in it. If you go and measure it, so if I have an electron confined inside of a box, I know it's inside this box, that puts a limit on delta x. Delta x is not infinitely big, which means delta p can't be infinitely small. You go and measure the momentum, you'll measure something, measure it again, you'll get something else, all right? And it's not because you're not measuring it right, it's because the momentum of that particle is not well defined. And if I want to know exactly where an electron is, I can't know anything about how fast it's moving. If I want to know exactly how fast it's moving, I can't tell you anything about where it is. And it's not because you're not making good measurements. Even in theory, you cannot measure the position and velocity of a particle simultaneously with arbitrary precision. All right, so uncertainty is one of the bizarre side effects of believing that everything is represented by a quantum wave. All right, so why would we believe such a thing? Well, because it works. All right, it gives us the right answers, and these uncertainty relationships have been measured. It happens. Am I right? It's real. Okay, so in quantum mechanics, we have this thing called the wave-particle duality. Things act as a wave when propagating, or in other words, we use waves to make our predictions as to where we might find a particle when we make our measurements, or what if I measure the energy, what energy will I measure? All right, so things propagate as waves, but then when I measure something, all right, if I measure a wave-like property, I'll get a wave-like answer. But if I measure a particle-like property, I'll get a particle answer. For example, have an electron. It's going to propagate through space as a wave. If I measure where it is, that's a particle-like thing, right? Where are you? A wave doesn't have a where are you. A wave is spread out. So when I measure my electron, it has to decide to be somewhere. So we say the wave function collapses. But the size of the wave function in space tells me with kind of what probability I will measure the electron at one place versus another. If the wave function is big, that means I'm likely to measure the electron there. Where it's small, I'm not likely to measure the electron there. But the important thing is these probabilities are not like classical probabilities. It's not a matter of the electron is somewhere, I just don't know where. In quantum mechanics, quantum uncertainty says the electron really isn't in a specific place until you measure it and force it to be somewhere. How can you tell the difference? Classical uncertainty doesn't interfere with itself. Quantum uncertainty does. It really acts like a wave. Okay, so quantum mechanics, the fact that things behave, that particles behave as waves, I've shown you several examples, experiments I've actually done myself that show that things behave as waves. But making things behave as waves also helps us answer some weird problems that people were having back at the beginning of the 20th century. All right? One of the problems that they had was that atoms should not exist classically. All right, so atoms consist of a nucleus and a bunch of electrons going around it, right? In the classical picture, these electrons are orbiting around the nucleus. Well, an electron orbiting a nucleus is accelerating, right? It's not traveling at a constant velocity, its direction's changing, and accelerating particles radiate energy as electromagnetic waves. All right, so you calculate, I've got a hydrogen atom in the ground state, in the kind of the some distance away from the nucleus, the electron some distance away from the nucleus. How long should it take for it to radiate away all of its energy and crash into the nucleus? Turns out the time to do this is a fraction of a fraction of a fraction of a second. All right? So we have two problems with classical physics. First of all, why do atoms even exist? Shouldn't all of the electrons have crashed into the nucleus by now? Another problem is when atoms radiate light, they only radiate specific wavelengths. All right? Kind of a classical picture would say, I've got this nucleus, and I've got this electron orbiting it, right? So this electron's moving at around in some frequency. It should make light at that frequency. And if I make the orbit a little bit bigger, the frequency will go down, and I should be able to get any wavelength of light depending on where I put the orbit. All right? But it turns out atoms only emit certain wavelengths of light. If you look at the light coming from a neon sign, only certain wavelengths, very specific wavelengths come out. And atoms only absorb certain wavelengths of light. Okay? But it turns out the wave nature of matter explains this. But before we get to the wave nature, let's look at Bohr's theory. Bohr didn't think about in terms of waves, but he came up with sort of an empirical way of figuring out what wavelengths of light atoms could absorb or emit. And this is what he said. He's postulated that there are certain orbits in which the electron doesn't radiate. So if you put the electron in a very specific orbit, that orbit will not radiate and our atoms will not cease to exist. And then he says, the light released when an electron changes orbits is a photon with an energy equal to the difference in the energy of the two orbits. So it's not light at the frequency that the electron is orbiting at, it's light at the frequency which corresponds to the energy that the photon has, and that energy is just the energy the atom lost when it went from one orbit to another. All right? He further postulated that these stable orbits were circular with quantized angular momentum of n(h bar). And when you do that, it turns out you find then that the energies of the hydrogen atom are just E0 over n squared, where n is just an integer, right? So n labels the different energy levels for your hydrogen atom, and E naught is minus 13.6 electron volts. So the ground state of hydrogen, the lowest energy, is when n is equal to 1, and its energy is negative 13.6 electron volts. Why is it negative? Well, because we're kind of assuming that zero energy is when the electron is separated from the proton infinitely far away. All right, so it takes 13.6 electron volts to pull that electron out of the hydrogen atom when it's in the ground state. All right, and as n gets bigger, 1 over n squared gets smaller, which means there's less negative energy holding our electron in, right? So the energy goes up as n goes up because E naught is negative. All right, so plug in some number, some integer for n, and that's an allowed energy for our hydrogen atom. So our hydrogen atom can't have just any energy, it's got to have one of these allowed energies. All right, so what is the wavelength of light? What wavelengths of light can be emitted by hydrogen? Well, you just say, well, the energy of the photon of light is just the difference in the energies of these two orbits, right? So you take, I start in state 1, where n is equal to n1, and you drop down to some lower state, n2, all right? And you subtract these two, right? These two energies, and you find the energy of your photon. And then, of course, we remember that E is equal to hf, so we can find the frequency of our photon. And for a photon, only for photons which travel at the speed of light, lambda is equal to c over f, right? So we can find the wavelengths of light emitted by hydrogen with Bohr's theory just by using this equation. All right, this tells us what wavelengths of light can be emitted. The ones that can be emitted are also the ones that can be absorbed. It's the same thing backwards. My photon has a particular energy. If that energy is just right to take me from the n equals something, say n equals 2 to the n equals 4 state, right? If the energy of my photon is just right, that it matches the difference in energy of two states, then my hydrogen atom can absorb it. If not, it can't. All right, so that's why hydrogen atoms only absorb and emit certain wavelengths of light. But I say why, but there's really not a why here. This is just sort of an empirical theory, right? So, for example, an electron falls into the n equal 2 energy state and a photon is emitted. If it falls from the n equals 6 state to the n equals 2 state, you plug it into the equations I showed before and you find out that that photon will have 410 nanometers. If it falls from the n equals 5 state to the n equals 2 state, it'll emit a photon with a wavelength of 434 nanometers, all right, and so forth. And so it turns out you get very discrete wavelengths of light coming from your hydrogen atom. Absorption of light, I mentioned, it's just emission backwards. So if hydrogen can only emit certain wavelengths, it can only absorb certain wavelengths because the wavelength of light has to be just right so that the energy of your photon takes you from one energy level to another. So if your hydrogen atom is in some energy level, your photon has to have the right energy to take it to another allowed level. If not, the hydrogen atom can't absorb it. Now, I hope all of this makes you uncomfortable. Quantum mechanics is weird. But mostly I hope that it makes you uncomfortable because Bohr theory is just kind of this random weird thing. You know, why would the electrons not radiate in certain states and whatnot? So, Bohr theory, I hope you realize there's a problem with Bohr theory because it's very empirical. It doesn't really give us new physics. It's just kind of a system that connects numbers together, all right? So because it's empirical, how do we apply it to other atoms? We've got this great theory for hydrogen. It's not a great theory because it doesn't apply to other atoms, all right? It doesn't even tell us everything we want to know about hydrogen. It doesn't tell us the line widths and the line strengths, right? So, you know, the colors that come out, the wavelengths that come out of hydrogen, they're not exact colors. There's a little spread. Where does that little spread come from? Why is it the thickness? Why do some transitions happen more often than other transitions? It doesn't tell us that. It doesn't tell us how hydrogen atoms get together to form molecules. And if it doesn't even tell us about hydrogen or completely, or really anything about other atoms, how does it tell us about things that aren't atoms, right? There's some new fundamental physics going on, and all we've got from Bohr theory is how to do a very limited set of problems. We really want to know what is this fundamental physics that makes Bohr theory look like it works. What's really going on? All right, and it turns out that Bohr's theory gave us a good hint as to what was going on. Even though Bohr theory is very empirical, it gave us a good hint. And it turns out what is going on is electrons behave like waves, just like Planck postulated, just like Davisson and Germer measured. All right? So here's Schrodinger's idea. Schrodinger comes along and he says, look, electrons are waves. These waves are probability waves. So the size of the wave tells us the probability of finding a particle at some particular place at a particular time. The electron is more likely to be where the amplitude of the wave is high. Okay, let me say the electron is not anywhere in particular, but when we measure it and force it to be somewhere, where we're likely to end up finding it is bigger. The probability is bigger of finding it somewhere if the amplitude of the wave is bigger. All right? So, why does hydrogen have quantized energy levels? Well, if the electron is a wave, and this wave is confined by the pull of the nucleus, it turns out that these waves have resonances. Just like an organ pipe has resonances, an electron bound to a proton has resonances. And you can sit down with a wave equation and figure out what those resonances should be, and you find precisely those energies that Bohr predicted. All right? Now, if an electron is a wave, it obeys a wave equation. This is the wave equation. It's a partial differential equation. It's probably very confusing. I only put it up for you because it looks really cool. But also, I wanted to point out the wave equation that electrons, well, this applies to any massive particle. It has the imaginary number in it. So the waves that describe massive particles, unlike light waves, electromagnetic waves, they have to be complex in their very nature. Another thing that waves do is waves tunnel. All right, imagine that I have a piece of glass and I have some light traveling into it, and I get total internal reflection. Well, it turns out, as I mentioned earlier, the light energy does kind of barely stick out the edge of the glass. All right, but it can't make a wave. It doesn't propagate out to infinity. It kind of just kind of hangs out the edge of the glass and then comes back. But if I put another piece of glass really close, you get what's known as frustrated total internal reflection, and you can actually get light going through even though you have this air barrier in between that ought to give you total internal reflection. Well, it turns out quantum waves can do that too. It turns out, imagine that I've got an electron, all right, and it's trapped inside of a piece of metal, all right, and the electron's energy is not high enough to get out of the metal. If I bring another piece of metal really close, it turns out that the wave function of the electron kind of sticks out the edge of the metal, and if another piece of metal is close enough, the electron can actually tunnel out, even though the energy of the electron is not big enough to get out of there. It's kind of like saying this. Imagine I have, let's draw a better picture. Imagine I have a ball and I roll it up a hill. And my ball has enough kinetic energy to make it this high up the hill. It could never get over the hill, right? But a quantum electron, a quantum particle, going up the hill, its wave function can kind of stick through, and it can kind of be here and then show up over here. And so an electron can get out of this piece of metal even though it doesn't have enough energy to, all right? It can't show up here because that would violate energy conservation, but it can kind of just show up over here. That's known as tunneling. And tunneling is pretty cool. The tunneling electron microscope uses this to make very precise measurements of things, all right? So the idea in a tunneling electron microscope is you have a little metal tip, you move it over a surface, and you put a different voltage here, and the electrons want to go down here, but they can't because there's no conductor. But they can tunnel through. And the rate that they tunnel through depends on how far apart, how big that barrier is they have to go through. So by measuring the tunneling current, you can make very precise pictures of things. So here is a scanning tunneling microscope image where they scan this tip over some material, and they're actually able to see individual atoms, detect the positions of individual atoms. All right, and here they're actually able to pick up atoms with the tip and then go and measure them and see they're actually able to write things with individual atoms. And this right here is known as a quantum corral. Each of these little bumps here is the scanning tunneling microscope measuring the position of atoms. They stuck atoms on a surface in kind of an oval shape here. All right, these ripples in here, those are the wave functions of electrons trapped inside of these atoms right here, and they can measure that with their scanning tunneling microscope. So tunneling is something weird that quantum mechanics allows things to do. All right. I have told you everything you need to know for the homework, but to put it into context, I hope you'll listen a little bit longer. All right? So quantum mechanics. The postulates of quantum mechanics are a little more complicated than the postulates for special relativity, but here they are. First of all, we believe that every physical realizable system is described by a state or wave function psi that contains all accessible physical information about the system in that state. So a system, physically realizable system, that's you, me, an electron going around a hydrogen atom, anything can be described by this wave function. All right? Another postulate of quantum mechanics is that the probability of finding a system within some volume dV at time t is equal to the magnitude of psi squared times dV. In other words, how big the wave is somewhere tells me about the probability of finding the system there if I measure it. All right, but remember, the system's not in any given place. It's kind of lots of places, just like my cesium atoms that travel two paths in a cesium interferometer. All right, they're not in one place or the other. They're kind of in a mixture of the two. But if I measure it, it has to force it to be somewhere. Where it ends up being is going to be related to how big the wave function is everywhere. Now, every possible observable is represented by an operator which is used to obtain information about the observable from the state function. An operator is something that just takes your wave function and does something, like multiply by 4, that's an operator. Take the second derivative with respect to x, that's an operator, all right? And there is an operator that pulls out any possible thing you could measure from your wave function and tell you the probabilities of measuring that. And then the final postulate is that the time evolution of a state function is determined by Schrodinger's equation, which is that hairy wave equation I showed you earlier. Now, quantum mechanics is weird, all right? What are some of the weird things about it? Things are quantized, right? It's weird that hydrogen atoms give very specific colors of light. That may not seem weird to you because you don't have a lot of experience with hydrogen atoms emitting light, but you do have experience living on Earth. And the fact that things are quantized tells us that the radius of Earth's orbit can't be changed by an arbitrarily small amount. There are specific energy levels the Earth can be in. Now, because the Earth is very large and orbiting at a very large distance from the Sun, the amount you have to change the orbit by, these quantized amounts, are very, very small, so you'd never notice it, like less than the size of a proton small, right? So it's not a big deal for Earth. It is a big deal when we talk about a hydrogen atom or any atom, all right? But the idea is these principles that apply to atoms, they should apply to big things as well, and that's kind of weird. Another weird thing about quantum mechanics is things don't have to be in one place, all right? You can take a cesium atom and make it travel two different paths and then come together and interfere. And in that interference pattern, you can find out things about the two different paths, all right? That's really weird. The particle can be in a superposition of being in two different places. And just this idea of superposition is really weird. So in quantum mechanics, you don't have to be in a particular state. You can be in a superposition of states. If you go and measure something, right? If you measure the energy of a hydrogen atom, it has to give you one of the allowed energies. But until you go and make that measurement, it can be in a superposition of different energy states. Schrodinger came up with an interesting thought experiment to kind of help illustrate how weird that is. So imagine this. I put a cat into an ideal box, one in which no information can flow in or out. I put it in there with a bottle of poison. A device in the box will open the bottle and kill the cat when a radioactive atom decays. All right? So now I'm coupling the cat's life to something which is very microscopic and quantum mechanical. All right? So there's some probability that this radioactive atom will decay in a certain amount of time and kill the cat. All right? So after the cat has been in the box for a time t, is the cat dead or alive? Is your answer yes or no? I want you to think about that for a while. Maybe pause the video, come back when you have an answer. Okay, are you back now? Some of you are probably thinking, those are not good answers. The answer should be dead or alive, right? No. My question is the cat dead or alive? And the correct answer is no. The cat is not dead or alive. The cat is in a superposition of being dead and alive. It won't be in one of those states purely until somebody measures the cat and forces its wave function to collapse into one or the other of these different pieces of the superposition. Now this seems really, really bizarre, and no one's been able to do this experiment on a cat because cats are big and have many degrees of freedom. But very analogous things happen when we do experiments with atoms and with individual photons and electrons. All right? And presumably these laws still apply to big things. So it's something to lose a lot of sleep about, I would think. Okay, why do you care about quantum mechanics other than the fact that it's really neat and bizarre? Well, you need it to understand small things, like transistors in computer chips and red blood cells. So there's a lot of very practical applications, a lot of things that you use every day, and things that are very important to our modern world, which you cannot understand without quantum mechanics. It turns out there are things that aren't small, though, that also require quantum mechanics. We call these degenerate things, things where the quantum mechanics, normally when you have something really big, all these degrees of freedom get out of phase with each other, incoherent with each other, and the quantum mechanical nature kind of washes out, and classical physics is enough to explain it. But there are certain things where the quantum doesn't wash out. Like laser beams are quantum mechanical things. They are not classical light. They are quantum light. You have to understand them with quantum mechanics. Neutron stars, it turns out they're huge, but the enormous pressure acting on the neutron stars, it turns out the quantum mechanics is required to explain why neutron stars don't just collapse. Okay? So you should care about quantum mechanics because you need it to understand and calculate and build and use some really important things. There's also some really interesting things you can do with quantum mechanics. Go to Google and Google quantum computer, and you will find that there's a lot of research going on using this idea of superposition in computers. Imagine, if you will, you have a memory register. It's a bunch of ones and zeros, right, that represent a number. What if that register could be in a superposition of a bunch of different states? So this bit right here is not a 1 or a 0. It's a superposition of 1 and 0. It turns out there's some interesting things you could do if you could make a computer register that could be in superposition states. So with a quantum computer, there's certain things you should be able to do really fast, like break encryption keys. All right? Okay, quantum mechanics also gives us a solution to people using quantum mechanics to break encryption keys. You can actually use quantum mechanics to encrypt things. All right, so you can use quantum mechanics to make sure that nobody can eavesdrop on a conversation that you have over some quantum channel, right? So if you want to send some information to somebody in another country and not have anybody have any chance that anyone can intercept it, it turns out quantum mechanics gives you a way to do that. Now, neither of these applications are easy, and people have been working on them for a long time, but there's some cool potentials. So go to Google, Google quantum computer, Google quantum cryptography, and read about really interesting things. All right. Hope you've enjoyed quantum mechanics. I hope it blew your mind, but hopefully not to the point that you're not able to do the homework in the exams. Good luck.